Hello guys, welcome back on African Motives, still on mathematics N3, working on exponents and logarithms. We have got a question that you're going to consider. That is something about 16 marks that you're going to work on in this class, where we are given from the question paper of August 2017. Question 2, 2.1, simplify the following expressions. The first month, part 2.11, that was actually having 4 marks. All right, so let us check our question, the one that you're given on 2.11, this part. So I'm just going to put it this way so that you can properly see. All right, so the first part we are given to simplify this whole expression. So what we need is to ask ourselves, what is it exactly that we are given and how can we simplify this part? Given the first part that we've got 1 over a plus b to the exponent of, take note, this is -1, then minus a to the exponent of a half minus b to the exponent of a half, everything to the exponent of a 2. All right. So the first thing, as we can see here, we've got to the exponent of a -1. That is one that we need to talk about in this case. All right. What can we do with this to the exponent of -1 from the concept any number raised to the exponent of a -1 simply means 1 over x to the exponent of -1 is 1 over x. From which concept x to the exponent of minus a is 1 over x to the exponent of a. So meaning to say here we are going to have the bracket of a plus b, which is raised to the exponent of, but take note already there is a 1 over that we are given here. So this is going to be something like this, 1 over. Then we have got this part of a plus b to the exponent of -1. The one that I'm saying is same as 1 over x. So it is going to be 1 over like this. A plus b to the exponent of a 1, which is just same as 1 over a plus b. Now, what is it that we are having? It's a fraction with the 1, 2, 3 elements. So what can we do? 1 over a over b, 1 divided to a over b. I explained before that this is the same as b over a. 1 over simply means the inverse of, you simply invert your fraction. So if I'm given 1 over a plus b, this simply means the inverse of this denominator part. So we are going to have a plus b on top, a plus b over 1, of which a plus b over 1 is same as a plus b. All right, so this means, guys, all this part that we have been having, the first part of our expression, this part, simply represents a plus b. This is what we have from this part. All right, then we have got minus a minus b. This is everything a to the exponent of a half minus b to the exponent of a half, everything being raised to the power of 2. Never be tempted yet to raise a to the exponent of a half to the exponent of 2, you get a. B to the exponent of half to the exponent of 2, you get a b. This is actually wrong. Take note, guys, from our expansion, if I'm given this, is either I'm expanding the brackets or I'm using the concept that we know that a minus b squared is equal to a squared minus 2ab plus b squared. We are supposed to have this identity, and also the one for addition, a plus b squared, which is equal to a squared minus 2ab. So this will be a plus here, plus b squared this time. So if we check, this is what we are simply having. So meaning the first part, we are just going to have it as it is a plus b, this part minus. All right. So what we need is to expand the a minus b to the exponent of a half squared, which following a minus b. So we are going to have a squared. So this is our a, which is the first part here, but raised to the power of 2. So it is going to give us a squared, that is our a, is a to the exponent of a half to the exponent of 2, that is a squared. So a half and a 2 multiplies. Remember from your laws of exponents, x to the exponent of a to the exponent of b gives us x to the exponent of ab. So here we are going to multiply a half and a 2. So half of 2, that is a 1. So this is a to the exponent of a 1, which is same as a. So we're going to obtain a minus 2ab. So this part we are saying we are going to multiply minus, from this concept, it's minus 2ab, meaning to say we are going to have a -2 They're like this. A and B, this is our A, which is A to the exponent of a half. Our B, it's a B to the exponent of a half. And there's nothing that we can do unless maybe you want to combine this to a single term where because we have got the same exponent. So we can write this as a single term. Remember, mn to the exponent of A is same as m to the exponent of A, n to the exponent of A. So you can write as a single exponent, which is going to be -2. So this part can be written as -2ab, everything to the exponent of a half. That's if you want to write it that way, or you can just leave it as -2a to the exponent of half, b to the exponent of like that. All right. Then the last part that we have on our expansion is now at b squared. So we talked about a squared minus 2ab, then b squared. So b squared follows the same way just as a squared. It's a b to the exponent of a half, then to the exponent of a 2. So still this is going to give us b a half, and a 2 gives us 1, which is b to the exponent of 1, which is a b. Or this part you could have just expanded in a normal way, where you can just open two brackets. This is a squared, so we're going to have two brackets of a to the exponent of a half, b to the exponent of a half, into another bracket, a to the exponent of a half minus b to the exponent of a half. So you can still apply the same concept, you obtain the same thing. So here we are going to multiply a to the exponent of a half and a to the exponent of a half. We are multiplying the bases, which are the same. Remember, you add your exponents. So a half and a half gives us a 1. So this is going to be a to the exponent of a 1. We move on. We multiply a to the exponent of a half and minus b. So this is a minus a to the exponent of a half, b to the exponent of a half. We are done with a. We move on to b. So this is minus b to the exponent of a half times a, which is going to give us minus a to the exponent of a half, b to the exponent of a half. The same concept here. We multiply the last part, minus b to the exponent of a half times minus b. So it's minus, which is a positive. So that will be positive b to the exponent of a half. And if we add our like terms, sorry, this is a half and a half. So we add, this is going to give us a 1. Half plus half, that's a 1. So we are going to add, combine the like terms. These are the like terms. As you can see, these two are the same. So this is -1. This is -1. So if you combine, a to the exponent of a 1 is same as a. So here we're going to have -1, which is -2. A to the exponent of a half, b to the exponent of a half. Then plus b to the exponent of a 1 is same as b. So as you can see, this part that we have is the same part that we got after expanding using these identities direct from our algebraic part, these identities. So you can just expand direct, or you can expand the brackets as this part. All right. But anyways, after expanding, you can see that here we now have brackets from the quadratic expression that we had, which was raised to the power of 2. So we are going to expand the brackets now with a negative that is outside of this bracket. It must affect each and every term. So it's minus times a, which is minus a, minus times a minus. Here it's going to be a positive 2. Remember, I said you can combine this everything to the exponent of a half. Then minus times a b, which is going to be a negative b. So from this part, we can collect like terms since we have expanded our brackets. We've got 1a and a, negative a. So this is same as 1a minus 1a, which is a 0. So this one gives us a 0. Same thing with b minus b. This also gives us a 0. So we are remaining with the 2ab to the exponent of a half, which we can also write as, remember, to the exponent of a half is same as square root of. So we can write this as the square root of. So this can be written as 2 square root of AB, the A and the B, everything under the square root. So these are the typical questions actually that you might have, or that you might be given. So all you need is to play around with the laws of exponents, logarithms, and not just logarithms, also to work with your algebra back to your equations, factorization, expansion of brackets. Everything has to be in conjunction so that we can answer these typical questions. All right, that was our question 2.11. Now 2.12 we are given again to simplify. So this is to simplify. again. All right, so let us just remove this part so that we can simplify this part here where we are given the square root of 4 to the exponent of n plus 1. Okay, let me just rewrite this aside. So this is 2.12, the square root of 4 to the exponent of n plus 1 times the cube root of, so this is the cube root of 8 to the exponent of n plus 1, everything over 4 to the exponent of n minus 1, just to simplify. So when you're asked to simplify, you need to know exactly what to do with the laws. All right. So with the laws that you are given in this case, I want us to check properly. We have got exponents here, and we have to apply the laws of exponents. So let us start with the square roots, the cube roots that we have here. Remember that x, if raised to the exponent of a over b, gives us the bth root of x raised to the exponent of a. So meaning to say here we've got the square root of x, which is same as to the exponent of half. I think this one we are now used to this. So that's 4 to the exponent of n plus 1, which was there already, but now everything is going to be raised to the exponent of a half. Or we can just have it this way. Let me just remove this part and raise the bracket. We can just have our bracket n to the exponent n plus 1 like this to the exponent of half, easy like that. All right, the same thing multiplied to 8 to the exponent of n plus 1. The first thing that we have, it's 8 to the exponent of n plus 1 inside, that's n plus 1 like this. But if you check, we've got the cube root of that, the cube root. So the cube root means to the exponent of a third. So whatever that you are going to have here, we are going to multiply or to raise to the exponent of a third. That's the cube root of to the exponent of a third, 1 over 3. All right, so we have removed the cube root, we have removed the square root, everything over 4 to the exponent. We do not have a square root or a cube root. Okay, we are not simplifying in simplest form. We are just talking about the square roots in this case. Yes, so we are going to talk about now simplifying in simplest form, this and that. All right, so if we check here, we can simplify direct in simplest form, or we can first expand by the exponents that we are given. So you've got two options. It's either we are going to expand by to the exponent of a third each and every term, or you can write this in simplest form, 4 in simplest form, 8 in simplest form, 4 in simplest form. That is the simplest way that we can use, or the base that we can work with for 4, 8, and 4 is the base of 2. So if we are talking about the base of 2, that means the 4 here can be written as 2 to the power of 2 in base of 2. 4 is same as 2 to the exponent of 2. So that means here we are going to have this as 2 to the exponent of 2 into the bracket of n plus 1, but also we have got the exponent of a half. All right, I'm going to explain this later on. 8, same 8 in base of 2, that's 2 to the exponent of 3. So we've got 2 to the exponent of 3 to the exponent of n plus 1, that was there, times the exponent of third, which was already there, this one, okay? Then we move on to the other part here. We've got 4 to the exponent of n. So in the base of 2, we said 4 is same as 2 to the exponent of 2, but we've got the exponent of n minus 1. All right, so this is what we are having, or this is what we are going to get here. 2 to the exponent of n minus 1 times a half. These are just numbers, so you can multiply 2 and a half, which gives us a 1. Remember, 2 times a half, that's a 1. So we are remaining with a 1. So 1 times n minus 1 is just going to remain as n plus 1. I mean, that's n plus 1. So this is going to be 2 to the exponent of n plus 1 multiplied to the same thing here. 3 times a third cancels, that's a 1. So you're going to remain with n plus 1. So this will be 2 to the exponent of n plus 1. Then for this part in the denominator, we've got nothing to cancel, but we can simplify further since we have got the bracket here. So 2 can expand the bracket. That is 2 multiplying each and every term. 2 times n, which is going to be 2n. 2 times negative 1, which is going to be a negative 2. So from this concept, from our laws of exponents, if you are multiplying the bases which are the same, we know that we are going to add the exponents. So that will be x to the exponent of a plus b. If we are dividing, we know that in this case, we are going to subtract the exponent. That's x to the exponent of a minus b. So meaning to say, The top part we are multiplying, so we're going to add the exponents, n plus 1 plus the exponent of n plus 1. So if we are adding, there's no need for us to open the brackets if we are adding, all right? But now, if you check the same base of 2 that we are talking about, which was multiplying on top, in the denominator this time, we are going to divide whatever that you get, you are going to divide by the same base. So if you are dividing, we said we are going to subtract. So we are going to subtract what is in the denominator from the base, which is 2n minus 2. So here we are going to subtract. We open the bracket for that, which is for 2n minus 2. So take note, on subtraction, it must affect each and every term. A plus does not change the sign, does not affect the sign. So that's why it's not important for us to open brackets. Yes, you can do that, but it's not that important. All right, this is what you're having. Let us try to simplify further. We have combined from the numerator, we combined everything with the denominator. So all we need is to simplify to get the final answer. This is 1. This is 1. So you can add 1n plus 1n, which is going to give us 2n. So that's 2n. Then we've got 1 plus 1 here, which is going to give us a plus 2. All right, let's expand our brackets. Negative is going to affect 2n and is going to affect a negative 2. So this is going to be negative times 2n, which is negative 2n. Negative times negative 2, which is going to give us a positive 2. All right, so from this part, we can collect our like terms just like the previous part. Again, we've got 2n minus 2n, that's a 0, 2n minus 2n. So we remain with the 2 plus 2. So if we add 2 plus 2, that's a 4. But remember, this is under the base of 2. So we are having 2 to the exponent of 4, which we can simplify. 2 times 2 times 2, 4 times gives us a 16. Or we can just use our calculator direct to simplify 2 to the exponent of 4. So these are the stages that you're supposed to have in your simplification. Take note here, we are not bounded to not to use anything, or it's just to solve. So meaning to say we can even have our calculators as assistants in terms of multiplication. But as you can see, this is what we could have done to answer this question. Let us check the other part of our question, which is still on solving. No, this one is now solving. The first part was just simplifying. 2.2 is to solve. All right, so let us check what we got on question 2.2, where we are given this time to solve for x if the logarithm of 10 to the exponent of x plus 2 is being equated to 2x plus 1. All right, this is a log equation. Yes, we all agree that this is a log equation. But how can we get about this? We are given a log on the left-hand side, a normal expression on the right-hand side. So how can we convert this into an equation that we are used to? If we were given the logarithms on both sides, let's say log A base B is equal to the logarithm of C in base of B. If we were given a condition like this, we're going to work with this condition to say if the bases are the same, you are simply going to equate these numbers, that A is equal to C. But we do not have a log on the right-hand side. So meaning to say this one, we are limited. We can't apply this. So which concept can we think of? Let us think of having a logarithm on one side, then a normal term on the other side. The logarithm of A in base of B, if it is equal to C, I explained before that this is the same as the A that we are having is equal to the base, which is our B, to the exponent of C. So this is same as B to the exponent of C, which is in exponential form. This is a log form. This is an exponential form, which can be converted from exponential form back to the log form. So this is what we have. Which base do we have here? It's base of 10. If the base is not given, it means we are in base of 10. So this is our A, this whole part, 10 to the exponent of x plus 2. This is our A. So we said A is equal to, so that's 10 to the exponent of x plus 2 is equal to the base to the exponent of C, our base, which is 10 to the exponent of our answer. So this will be 10 to the exponent of this answer, which is 2x plus 1. So we are now having an equation which has nothing to do with the log that we had. This is just a normal equation that we are supposed to solve. Which type of an equation this? This is an exponential equation that we now have. From the log equation that we had, we created or we formed an exponential equation. We do not have any log in this case. This is just a direct exponential equation. So how can we solve? All right, considering this part here, the left-hand side, there's actually nothing that we can do further. Let us just rewrite as it is 10 to the exponent of x plus 2 is equal to, let's consider this part. We are adding 2x plus 1. Which concept made us to add these two? It means we were multiplying the bases, which are the same. X to the exponent of a times x to the exponent of b gives us x to the exponent of a plus b. So if we separate the a plus b, this one, back to its original terms, it means we are multiplying bases which are the same. So meaning to say here we are multiplying 10 to the exponent of 2x multiplied to 10 to the exponent of 1, just like x to the exponent of a, x to the exponent of b. So this was being multiplied to 10 to the exponent of a 1. So now if you check, this is an equation that we can just multiply, or that we can just choose to let 10 to the exponent of x be equal to a certain term. Since here we can, okay, let me just transpose these terms to the right-hand side, all these terms, meaning to say, yeah, I'm going to have 0 is equal to 10 to the exponent of 2x multiplied to 10 to the exponent of 1. 10 to the exponent of 1 is same as 10. So this is 10 times 10 to the exponent of 2x. But I want you to see what is happening with 10 to the exponent of 2x. We want to write it as 10 to the exponent of x. So this is same as 10 to the exponent of x, but raised to the exponent of 2, such that x times 2 gives us 2x. From x to the exponent of a to the exponent of b, which gives us x to the exponent of ab. So we can separate this. X times 2 is 2x. So what I just need is to write this as to the exponent of x, like this part, all right, to the exponent of 2. So this is what we have, what we had from our right-hand side, this part, all right? So like I said, I'm going to transpose the left-hand side to the right-hand side. So 10 to this side is going to be a negative 10. That's negative 10 to the exponent of x. 2 to this side becomes a negative 2. So as we can see, we now have a normal equation of a quadratic, an exponential, but in form of a quadratic with exponents. So in order for you to avoid these equations, introduce a constant. That's why I'm writing these in the same format, so that we can introduce to say, let k be equal to 10 to the exponent of x. With this, I can substitute where there is 10 to the exponent of x with a k. Like this, I'm going to have 0 is equal to 10. 10 to the exponent of x is written with, is now written as x, so as k. So this is 10k, but there's an exponent of 2, so that's 10k squared. Minus, in this case, I've got 10 to the exponent of k, which is representing 10 to the exponent of x, which is representing k. So this is minus k minus 2. We do not have 10 to the exponent of x. So as you can see, this is a normal equation that we are given, which we can solve for a for k in this case. Remember that if we say a is equal to b from this format, if a is equal to b, then it means also b is equal to a. So from this part, if 0 is equal to the right-hand side, it means we can start by writing the right-hand side on the left-hand side. 10k squared minus k minus 2 is equal to 0. There is just one in the same thing. So you can solve. How are you going to solve this part? It's up to you. It's the method that you are used to. You can work with factorization. We can work with quadratic formula, as long we've got the values of k. But according, mostly in our syllabus, we've got application of the factorization method. So from our factorization, this time the coefficient of k squared is not a 1. So what you're going to do is to multiply the first term of our equation to the last term of our equation in this case. All right. So this we are going to multiply with the last part, which is a -2. So that's 10k squared times -2. It gives us negative 20k squared. So what you need is to find factors of negative 20k squared. So we need the factors here, factors. Then two terms, you multiply, you get a negative 20k squared. But if you add these two terms, they must add up to negative k, which is same as negative 1k. So what you think of are the numbers first. Before thinking of k, think of the numbers. So you can think of 5 and 4, but we are going to have this as negative 5 and 4. All right, if you multiply this, we get a negative 20. If we add negative 4 plus 5, we get a negative 1. But for us to obtain k, we are going to have it as minus 5k as 4k. So these are the two terms that we are going to replace into the middle term, which is the minus k. We are going to substitute into this middle term, meaning the first term is going to remain as it is, as 10k squared. Then our middle term is going to be replaced with these two terms that we multiplied to get that term of minus 20. But if we add, we get negative k, which is a negative 5k plus 4k, like this. All right. Then the other terms, like we saw, the first term and last term, they remain as they are. So this is equal to 0. So remember, from your factorization, once you've got an expression like this, you can factorize by grouping that is into two terms. The first two terms, what is common between 10 and 5? That is 5k. So you're going to divide 10k squared divided by 5k, which is 2k, minus 5k and 5k. If we divide minus 5k and 5k, this gives us a negative 1. All right, remember, you're supposed to have the same thing from the second bracket. If you factorize between 4k and positive 2, so we are going to factor out positive 2 as our highest common factor. So plus 4k divided by plus 2, this gives us plus 2k. Minus 2 divided by a positive 2, this is a negative 1, equal to 0. So as you can see, the two brackets are the same. So you're going to factor out the common bracket, 2k minus 1. If we factor out this bracket, we remain on this term with 5k. So you're going to remain with 5k. On the other part here, we are going to remain with a plus 2. So this is going to be plus 2. So this is what we have, equal to 0. So remember, from our 0 concept, each bracket must be equated to 0. So if 2k minus 1 is equal to 0, or 5k plus 2 is equal to 0, we can obtain the values of k. Transpose negative 1 to this side becomes a positive 1. So we can divide 2k is equal to 1 divided by 2 by 2. K is equal to 1 over 2. The same thing, if we transpose the 2 to the other side, it becomes a negative. So that will be 5k is equal to negative 2. All right, so from 5k is equivalent to negative 2. What we can do is to divide, all right? So this is a negative 2 here, so you can divide by 5 both sides. So our k is going to be negative 5 over 2. All right, so we have got our value of k being negative 2 over 5. So these are the values of k, not the values of x. So what we need is to go back to our introduction, where we introduced the k in the equation. Remember here, where we introduced our k, we said let k be equal to 10 to the exponent of x. We are supposed to be solving not for k, but for x. Our equation is for x. So we need to go back where we introduced our k. We said k is equal to 10 to the exponent of x. So that's where we are going to start. All right, so since here, all right, so let me just have it here. So since our k is equal to 10 to the exponent of x, so it means I'm going to take the first part here, equate to 10 to the exponent of x. So 10 to the exponent of x is equal to the k that we got, which is 1 over 2. The same thing here, our k, which is 10 to the exponent of x, must be equal to the k that we got here, which is negative 2 over 5. But as you can see, guys, we need to solve for x. And this here, we can't make these two to be in the same base. So what we need is to introduce our logarithms. So you can introduce a normal log like this, or you can introduce a ln, depending with what you want. So in this case, I'm just going to introduce log both sides, log both sides. All right. So remember, from our laws of log, if you've got an exponent, you drop that exponent. to multiply the log, that's x log 10, which is equal to the logarithm of a half. All right, you can divide by log 10, but no, guys, logarithm of 10 is same as a 1. So if we divide by log 10, there's nothing that you're actually doing here. You are simply having the same answer. So our x is going to be log half divided to the log of 10, which same as log a half. So this is going to give us a log which is negative 0, 301, 029, and so on. So three decimal places, that's negative 0,301. That is depending with the degree of accuracy that you're given. But if you check on the other part here, we do not have any solution that can actually be obtained, because the moment we introduce a log, remember that there is no log of a negative number. The log of negative 2/5 do not exist on your calculator. That's actually a maths error, meaning to say we can't simplify this any further. So therefore, our x is going to be obtained from this part of 10 to the exponent of x, which was equal to a half. And from this part, we are obtaining, or we are seeing that our x therefore is going to be equivalent to negative 0,301 to 3 decimal places. All right, so that was our question. These are the typical questions that you might be given. And as you can see, this question with a lot of steps actually that we have to consider, but all you need is to apply your laws. As long you are applying the laws, so like we can see here, our question was having 7 marks. That's why. So let us continue to revise as much questions as we can as we are preparing for the exams which are ahead of time. But for now, guys, that's it from Maison African Motives. Till we meet again.